Hello everyone, welcome to this session. My name is Wycliffe, and in this video I want to share with you how you can utilize GIMMS Normalized Difference Vegetation Index dataset, which is available since 1982, between 1982 and 2022. So this is a good dataset which is available in OSAMG community catalog, and it's available twice a month. So we have 22 images per year at a resolution of about 1 out of 12th of a degree. So that's about 10 kilometers at the equator, right? And its primary objective was to address the uncertainties that were prevalent in long-term global NDVI datasets. So this data has got a quality control into which users are strongly advised to use quality control because it's generated, especially the consolidated one is generated based on machine learning process on a lot of Landsat datasets, like about 3.6 million datasets from Landsat were used in creating this image or developing this image. And yeah, that's what they indicate in their main paper, that 3.6 million Landsat NDVI samples were used to build the model and to make predictions. Now, it's as accurate compared to the earlier version of the dataset. It's more accurate, 0.97 root mean R squared and root mean square error of less than around 0.05. And you can read this paper to know more about the dataset. The dataset is also available on Zenodo, but I think one of the most important thing in Zenodo, where they put their data, is the metadata, this README file. It's important because it's the one that highlights how you can check on the quality, or what do you consider quality pixel, good quality pixel to keep, and bad pixels to remove. Okay, so let's dive into R and see how we can obtain this data and utilize it for our analysis. Remember, it's suited when you are considering large areas, like if you're modeling NDVI change for a whole biome. It may not be suitable when you are using a very small, when you are modeling a very small area, or when you are modeling, for example, a small farm, just one field. It may not be the best because it's at 10-kilometer spatial resolution. And if you resample this, or if you bring down, or if you want to make this very low resolution a high resolution data set, it won't yield much, because what you are doing is you are just breaking a big pixel into smaller parcels, but that really does not improve the quality of the data as such. You are just resampling it to get what you can use within your location, but it's not really improving the quality of the data. So maybe you can do that just for visualization improvement. Other than seeing the whole pixels, you see some bilinearly resampled values or pixels. Okay, so let's get into it. So as usual, we start by loading our library. So library rgee, and then library tidyverse. Why did I speak too much about this before we started coding? Because this was a special request from one of us, that we learn how to use this dataset, especially when it comes to cleaning it for the quality part. All right, so in this OSAMG community, there is a ID for the data, which we can just grab. I will pick only the consolidated due to time. Processing basically is almost the same as when we use the other version. So I will just call it maybe console for now. And then we don't need the semicolon at the end, and we need a colon. So with that, we shall have loaded the data set in R. That's the full name, and you can find it in the awesome G community catalog. Now, this image, in the this image as it comes, it has band 1 and band 2, whereby band 2 is the quality band and band 1 is the one for pixels, but it is not explicitly mentioned. So this is something which I think was a hitch when the data was being imported into G base or database, that the band names were lost. So we only have B1 and B2. That makes it difficult to tell which one is the quality band and which one is the NDVI band. But if we look at other information about the data like scaling and all that, we notice that the valid range, for example, for NDVI is between 0 and 1,000. Of course, this is uint 16, so meaning these values, we need to scale them down by multiplying by 0.001. Normally, they are saved as integers to save on memory, because if you were to save this as float, it will take a lot of memory. So this is a normal thing. But a serious missing thing is the names of the bands. They didn't talk much about the names of the bands. They are just provided as band 1 and band 2. As we can see, what can I do here? If we pick an image from this collection of console, if we take even the first one, because when we say first, normally we get an image. So if I write IM, that's an Earth Engine object, which is an image. So from this first image, we can extract, for example, the pixel values and see them, how they look like. So let's say I have a small feature collection or a small feature, which is Earth Engine geometry or a geometry point, for example. And then this, my point is located at, say, 35 degrees, 0.37, whichever, 218. And then it's located at latitude 0.47255. It doesn't matter. So that's my feature collection, or my point. We can call it point. So if I have a point, then I can sample from that image to get a feature collection. So I can say from image sample using a point, and we know the scale is 10,000. That is well indicated. It is not point, but PNT. So we have a feature collection, so we can see what is in this feature collection, SSF of the feature collection. And then that gives us, for example, these two values, which means these are the two bands inside each image, B1 and B2. Nobody tells you that this is a quality check band, and this is an NDVI band. But if we look at the functions, if we look at the descriptions here, we can think that the first band 1 is the NDVI band, and then band 2 is the quality check band, because the values for the valid NDVI is almost tending to 1,000, and this location is predominantly a green forest environment. If I can show it on map, map $ add layer and then PNT, you will see that it's located somewhere which is basically a forest. Yeah, this forested area. The point is here. So we expect NDVI here to be quite high, not 0.2. So it would mean that band 1 is the NDVI band and band 2 is the quality assessment band. Okay, so once we know which band is which, then we can create a function to do the cleaning and get the band. So we will call our band, for example, mask quality check. And in that function, we take an image. Once the function takes an image, once it has taken an image, then we can get the NDVI band, which is from the image. Just select the B1, that is the NDVI band, and then the quality check band is from that image, select band 2. Because we have now checked, I mean, this is a piece of information that should be made very clear in the description of the image, especially here in the GE community. They should specify somewhere what band 1 is and band 2 is, but it's seriously missing. Okay, so once we have those, we can then extract the digits. The digits, for example, if we look at this quality band 209, 2 here is represents the regression method which was used, and then 0 here means it is a good quality data or pixel. Actually, we were extracting from a point, so that pixel is good quality. And then 9 here also confirms that it's good quality because 9 implies not available. If we look at this README file, it's a lot of energy to use it. So if we see 0, it means good quality NDVI product. 1 means it was spline interpolated, and 2 means possible snow cover on the NDVI GIMS. But then the one we are using, which is 1982 to 2022, actually, yeah, to 2022, starting from 1982 to 2022, this one here, we have a good quality on band 0, but then the first digit is all about the method which was used, whether it was random forest, linear function. So that is, in our case, it's a linear function. And then 2 means it is good quality. And then NA means not available. So that's still good data. Okay, that's considered a good data. So that's how we interpret these digits. They are not obvious to tell whether 209 and which other value will we get. For example, the next value can be 313. So 313 will not be a good image because it's a linear function. That's not a problem, but 1 here means it was spline interpolated in the quality check, so it's not good quality. And then 3 here also means from the MODIS side, it is cloudy. So that's how the 3 digits are read, okay? If you understand that, then we can now play around with the digit. So the digits say 209. We want to look at this digit across all pixels in an image. So we will take the quality check band, okay, which we have selected here, the QC band, and then we divide it. The pixel value we divide by 10. After dividing by 10, we flow it, which means we truncate it, remove the trailing decimals, and then we take the modulus of that. And this, for example, if we were to do it in R, we would say, for example, we take 209 and then we divide it by 10. Sorry, we divide it by 10. So in that we get 20.9. Then we floor that. So in flooring this, that's the same function from G. We also have floor in R. So we get 20. We do away with 9. Then we get the modulus of this. So the modulus of this, we cannot use mod. This is a function which we are only benefiting from back in the Earth engine. Here in R, modulus, we use double %, and modulus of 20 is 0. So if we return a 0, then that's a good quality pixel. I hope you understand that. We take the QC, we divide it by 10, then we floor it to remove that. And then whatever we get, the quotient we have there, we get its modulus. Okay, so that gives us a quality band, whether it's quality or not. So we will check whether it's 0 or not to return whether that pixel is a good quality pixel. On the other hand, for the D3, we will take the quality, the band or the pixel value, and then we just take the mod of that by 10. So the modulus of that by 10. So it means we would just take 209 and then modulus 10. So the modulus 10 of, if we divide 209 by 10, we get whole number and the remainder is 9. So that remainder is what we are interested in. Whenever we see a remainder of 9, then we know that's a good quality image. So either a 0 there and a 9 at the end. Those are the quality checks we are doing. The first digit, which is 2, we don't care much about. Okay, so once we have that, then we can proceed with our cleaning. So our good, for example, advanced high resolution radiometer value, we will take the second digit, which is equal, if it is equal to 0, or that second digit is equal to 9, because NA was also accepted as a good quality. Okay, so if D2, if this operation returns a 0 or a 9, then that's a good quality advanced high resolution advanced very high resolution radiometer. On the other hand, we can get a good MODIS data, the D3, and again we look whether it is equal to 0, or if D3 is equal to 9. Just the same. The difference is the digit, is the D we are taking, the quality check we are taking. This is for MODIS. The first one is for AVVHR. And therefore, good quality check in general, we get it if we have good AVVHR, and because both conditions must be satisfied, we have good MODIS. Okay, but then we also need to work on the NDVI. So we can say vegetation mask, because NDVI is when NDVI is greater than or equal to 100. To threshold the NDVI values. Additionally, it is recommended to apply a threshold of 0.1 for NDVI. But here we are working on the image before we multiply it by the scale factor of 1,000. So we still check for greater than 100 You remember the values range from 0 to 1,000 before they are multiplied by the scale factor. So I hope you get why we are checking only where NDVI is greater than or equal to 100. Then we can now have our image and we update the masks. So we only apply that on band 1. And then after taking band 1, then we update mask on both cases. The first case being good quality check, QC, and the second case being update mask on vegetation mask. Okay, so this function here is sufficient to help us clean our images. In summary, it picks the NDVI and the quality check band. And for the quality check band, it looks for the digits inside each pixel where we equate to 0 or 9. And those with 0 or 9 are good. In the last 2 digits of every pixel value of the quality check. And both must be satisfied, especially for this data set that's the consolidated one, which spans 1982 to 2022. So both must be satisfied to have a good quality pixel. And then we check for the non-sparse vegetation and things that are less than 100. So we only pick NDVI where we only reliably use NDVI values that are above 100. NDVI ranges from -1 to 1, I agree. But before normalizing that data, they are in the range of 0 to 1,000. So 100 marks the 0.1 if it is multiplied by 0.001. Okay, so let's run this function and see if nothing breaks. Okay, everything is fine. Then now we can apply it on our images, right, on the console. So we can say on this console, which is now clean, we clean the bands. We say console and then map. Map the function, which is mask QC. Okay. So we have console clean, which is a very, very clean image, bi-monthly image, twice a month. Okay, so for example, this is now clean data and you can go ahead and use it the way you want. But I want to give an example of an annual image, right? So we can make a list, which is a sequence of numbers from 1982 all the way to 2022, okay? But then the annual images, IMGS is fine. We take the years and then we map a function. The function we are mapping is EEUTILSPY function, as we normally do. And then this takes year from the years. That is, if it takes 1982, it takes 1993 and all that. And this year, it passes as an Earth Engine number. So E number, and then we pass the year. Once the year is an Earth Engine number, we can say, let's start at Earth Engine date. Sorry, from year, month, day, where year is the year and month is the first one and day is the first day of that month, because system time start is a property in the images if you go through the documentation. And then after start, what we do to this end is we increase the start by 1 year. So we fall in the second year. Now, an annual image, therefore, will be console clean. Console here is just for consolidated. Console clean, and then we console clean, and then we filter if we filtered it, whereby we move all the way from start to the end. And then after filtering date, we take the mean of that period, if we wish, or median, or whichever. Then band names are normally lost. So we can say at engine string of NDVI, for example, NDVI underscore. Then we cut or we add the year as an integer. So we have to format it as a 4-digit number, integer, but we need % here. Okay, so after that, we can rename it, the image, the annual image. We can rename it using what we have just created, which is band name, and preferably set the year as the year. Okay, so that will give us annual image. I think we've done that more than enough in this November challenge. Then what therefore are where are therefore our annual images? Our annual images is an Earth Engine image collection, which takes its values, its images from a list, and the list is what has been created as annual images. If you check annual images, it's an Earth Engine object list. So we consider it as a list of images, and from images is the function that brings it home. Then we convert this to some bands. It depends on if you want annual images, if you want monthly, if you want the data as it is without converting it into annual or something, you can use it. Now we bring in the bringing down of the values accordingly. Okay? The pixel values. So after that, we can clean the names if we want, or we can just go ahead and do some visualization. I think no need for cleaning the name. We've done a lot of that. You just take the old names and you map a function around them to clean them. Let's make some visualization, or let's check the names first. I know they have some 0, 1, 2, 3, 4 prefix, but that is what we could have cleaned, but because of time, we may not. So if we check band names and we get information from that, we will see numbers like, that's interesting. Why did we have only one image? Something happened. Our console is that, and image is this. Okay, I think this image here affected our output. Let me see. Those are not important. Then we take an im. Okay, we took an im, but then we used image. Okay, so we need to be careful here. Okay, let me just convert that to image, and then this is fine. Then we apply it on that, and we apply for years, and we check that. This should be fine now. So it was the im and all that. So if we check the band names again, now we have all the bands from 1982 to 2022, because the other one was, we picked it first. We had the image, and then here we only provided im without G. Okay, so these numbers are what I hate. I don't want to see this 0, 1, 2, 3, 4. So I normally clean them, but you can take that as part of your exercise, how to clean the names of images. Okay, so let's get to the beauty of visualization. So we can add layer with an Earth Engine object as our annual, but we just select one band. We can select which one, 0 NDVI 1982, 0 NDVI 1982, or if 83, it doesn't matter. No, but 83 will not be 0, will not start with 0. So let's respect that. And then we provide some visualization parameters, which in R we provide as a list where we specify the minimum value to be 0 and the maximum value. In fact, we should say the minimum value is 0.1 because of that thresholding. Then the maximum value is 1. Then we can provide a palette, which is just some good colors ranging from maybe red. These are characters. And then we go to maybe orange. And then from orange, we get to yellow. Finally, pale green and green and dark green. The range here you decide. And dark green. Just trying to see something which can better represent. Okay, we are having a problem. Okay, this is not 0, these are O. Okay, change that. Cool. So we are able to see the NDVI image of the year 1982, but then it has been quality checked. It is high quality now. We've masked out pixels that were either cloudy or were spline interpolated. And yeah, we have taken consideration of the quality check before we finalize this. Cool, so that's, you got it. You can do all other reductions you might want, like getting statistics over some region of interest. No need to do that, but maybe just a quick one. We can say from the global database of the world, which is a feature collection, we can get a data set, and then we pick global administrative layers number 2. And then from here, we just pick a small region of interest, which is from the world database. We filter, and we filter using Earth Engine filter where the name is equal to what we already have in mind. So administrative level 2 name being equated to a region I'm comfortable with. You can pick your own region, you can draw your own region of interest, and you can do everything you wish with the polygon you want. So annual images, we reduce regions. We reduce regions, and in reducing regions, we need to provide what we call a collection. Why is it not popping up? Collection, and the collection is ROI. Normally, when I hit Control Tab, they pop up. We called it annual. That's the problem. So now they should pop up. Yeah. And the reducer here is called EE reducer. We can pick whichever reduction algorithm or method we want. Mean, median, mode, standard deviation, variance, whatever. And scale, let's go with the scale, native scale. Again, I'm repeating, if you pick a lower value scale like 10 or 20 or 10 meter, you can extract that data, but it doesn't affect the quality of the data you are getting in the end. You are just slicing one big pixel into smaller pixels. And therefore this, you can use this kind of data to talk about regional analysis. I think they mention it in their paper. It is not suited for someone who wants just to see something, say, in their small piece of garden. For example, somebody wants to monitor this tea field here. You don't need this kind of NDVI data. You better go for higher resolution data like Sentinel or Landsat or Planet or any other data, but not this one. But if you want to talk about the increase in the Sahel dryness or seasonal or variability in the Sahel or shrinking of the Congo forest or Madagascar or something in Saudi Arabia, then yeah, this could be the data set for you, or something happening, more greenness coming up in Greenland. Those ones you can talk about with this data, but not somebody's small plot of land. Okay. I think that's something which the person who contacted me about this really wanted to get clear. So I hope it is clear. Yes, so we have the statistics. We can see them as simple features if we wish. So you can say at engine SSF, as simple as that. And then if you look at stats, you will get the mean. Too bad that we have a lot of NDVI for each year. We have annual NDVI for each year, how they have been changing over time. Okay, yeah, because we are, and then they have the names of all other administrative regions of the feature collection, and also the NDVI for each year. 1982, it was this. 1992, it was that. 93. What happened? Oh, okay, 83 is there. I was thinking like 83 is missing, but it is here. It's only the order of this X10 coming before X1. But anyway, I will add, if you go to my GitHub repository, you will find this code well written and well described and documented. Plus, I will add a section on visualization or creating the plot of these figures. As a bonus, I will also add the renaming of this annual to have a better band. We are just trying to save on time for this. Otherwise, I hope you are now able to specifically handle cleaning of this kind of dataset to get high quality pixels. Otherwise, some pixels could have values that are not high quality, could have values that should be discarded as cloudy or other factors. Okay, if you find this useful, please grab the link to this script in the description section of this video. I have also updated description of how to set up rgee in your Windows. If you're using Windows, I've improved the process, the code, what you need to do to get it set up, and I've included it in the README part of my, not sure if I can show that. Let me, if you go to my GitHub repository, and a repository for the rgee 30-day challenge, you will find a README describing clearly how you can set up Windows for R users, starting from installing Miniconda, what you need to have in the background until you have your rgee setup for Windows users. So I know it has been a pain, but yeah, this is a way which I've tried in several computers, clean computers now, and I've realized that it works. So you can rely on this. Thank you, and happy coding. Bye-bye.